Hello.
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 Hi.
Hi.
Shall we
Shall we
start with
start
your
with your
topics?
topics?
Yeah, sure. Thanks.
Yeah,
Yeah, you
yeah,
want to talk
please.
something?
You
You
want to
want to
say
say
something?
something?
I think that was I messaged you some of the doubts. That was a great thing, like because it is easy to write there.
Yeah,
Yeah.
yeah. Okay, I'll just
Okay.
start with
So,
the
so can you please
first
increase your volume a little bit?
volume.
Yeah,
Is
Is
it
it
better?
better now?
yeah, a little better.
Okay.
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 Yeah.
So
So
first you
first you
were
were
asking
asking
about
about
gradient
gradient
divergence
divergence
and
and
curl,
curl.
right?
Yes.
Yeah,
Yeah.
like normal formulas you might have already know the difference, right?
Yeah.
Uh,
Yes.
Oh,
Yes.
Normal
normal
gradient,
gradient,
then
then
divergence,
divergence,
then
then
there
there
is
is
stir.
stir.
These
These
are
are
all
all
some
some
operators,
operators,
and
and
it
it
would
would
be
be
difference
difference
between
between
acting
acting
on a
on a
scalar
scalar
or
or
vector
vector
or
or
tensor.
tensor.
This
This can
depends
depends
on
on
it.
it.
So
So
gradient
gradient
adds.
adds.
So
So
when
when
you
you
say
say
gradient,
gradient,
it
it
is
is
normally
normally
like
like
we
we
generally
generally
deal
deal
with
with
3D.
3D.
So
So
derivatives
derivatives
in
in
with
with
respect to
respect to
components.
components.
So this is how
How
it
it
would
would
look
look
like
like
compared
compared
to
to
divergence
divergence
effect.
effect.
So
So
if
if
there
there
is a
is a
scalar
scalar
phi,
phi,
so
so
gradient
gradient
of
of
phi
phi
would
would
be
be
something
something
same.
same.
It
It
just
just
gives
gives
the
the
uh, like
like
gradient
gradient
in
in
that
that
direction.
direction.
So
So
how
how
the
the
scalar
scalar
value
value
is
is
varying
varying
in
in
this
this
specific
specific
direction.
direction.
Okay,
Okay,
like
like
uh,
uh,
it's
it's
like
like
you
you
have
have
some
some
3D
3D
field
field
and
and
some
some
scalar is
scalar is
present.
present.
So
So
like
like
if
if
you
you
want to
want to
see
see
in
in
this
this
direction,
direction,
x
x
direction,
direction,
how
how
much
much
it
it
is
is
varying.
varying,
So
so
you
you
will
will
get
get
the
the
x
x
component
component
in
in
y,
y,
something
something
like
like
that.
that.
So
So
it's
it's
same
same
as
as
the
the
derivative
derivative
in
in
1D,
1D,
but
but
in
in
three
three
dimension
dimension
we will
we'll
have
have
all
all
the
the
three
three
directions.
directions.
So
So
according
according
to
to
the
the
direction,
direction,
we will
we'll
know
know
which
which
direction
direction
has
has
how
how
much
much
is
is
the
the
gradient.
gradient.
This
This
is
is
acting
acting
on
on
Just
yeah.
yeah.
actually,
Yes.
you said that it is same as derivative. That is what I want to confirm. Like gradient is same as derivative.
Yes,
Yes,
gradient
gradient
is
is
derivative.
derivative.
Yes.
Yes.
But uh, like from other sources, I found that it is the maximum change. Like if we are moving in one direction, the maximum change that we get, that is gradient. Like they gave example of a steeper or something like that, moving in one direction.
Okay,
Okay,
direction
direction
of
of
maximum
maximum
change.
change.
Yeah.
Okay.
Okay,
Okay.
okay.
Okay. At
At
a
a
point,
point,
if
if
you
you
direction
direction
of
of
maximum
maximum
change.
change. Uh, okay. So
it
it
gives
gives
the
the
you
you
are
are
saying
saying
that
that
it
it
gives
gives
the
the
component
component
in
in
that
that
direction
direction
wherever
wherever
that
that
changes
changes
maths.
maths.
It's
It's okay.
Sorry, it was
Yeah.
disconnected.
oh
Oh,
okay.
okay. Oh.
Yeah,
Yeah,
I
I
was
was
just
just
saying
saying
that
that
I
I
think
think
if
if
you
you
like
like
in
in
x
its
direction
direction,
if
if
this
this
is
is
the
the
gradient,
gradient,
then
then
probably
probably
it's
it's
like
like
if you
if you
combine
combine
it,
it,
you'll
you'll
get
get
the.
the.
Are
Are
you
you
present?
present?
Yeah, yeah.
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 So
So
if you
if you
combine
combine
this,
this,
you
you
effective
effective
would
would
be
be
the
the
direction
direction
where
where
it
it
should
should
probably
probably
it
it
has
has
the
the
more
more
where
where
it
it
has
has
the
the
more
more
gradient.
gradient.
Yes,
Yes,
I
I
guess.
guess.
Individually,
Individually,
this
this
direction
direction
it
it
has
has
these
these
components.
components.
Okay,
Okay,
in
in
that
that
direction.
direction.
Mhm. Yeah,
Yeah,
probably
probably
that's
that's
true.
true.
Yeah.
Yeah.
I think these are open sources, so they might be having said something wrong, but they are both they're like nothing maths related. But I see some videos of those who belong from maths background,
Yeah,
Yeah.
and
especially
Especially
the
the
uh,
uh,
you
you
can
can
watch
watch
this
this
YouTube
YouTube
channel
channel
which
which
is
is
on
on
Maths
Maths
3 Blue 1
3 Blue 1
Brown.
Brown.
I
I
don't know
don't know
if
if
you
you
know
know
about
about
this
this
channel.
channel.
This
This
is
is
they
they
explain
explain
these
these
concepts
concepts
very
very
well.
well.
Like
Like
in
in
this
this
their
their
series
series
on
on
linear
linear
algebra
algebra
and
and
calculus.
calculus.
okay, three blue, one blue. Okay,
Mhm.
Yes.
It's
It's
really
really
very
very
good.
good.
Like
Like
they
they
explain
explain
all
all
these
these
concepts
concepts
even
even
with
with
visualization.
visualization.
okay.
It's
It's
around
around
like
like
10
10
to
to
15
15
videos
videos
on
on
linear
linear
algebra,
algebra and
around
around
10
10
on
on
calculus.
calculus.
So
So
that's
that's
very
very
good
good
source, I
source, I
would
would
say.
say.
You
You
can
can
follow
follow
that,
that,
and
and
it's
it's
trustworthy
trustworthy
as
as
well.
well.
Okay, thank you for
Okay.
the yeah. Please go
Yeah.
Yeah.
ahead.
Yeah. And
This
this
gradient,
gradient,
you
you
can
can
just
just
see
see
that
that
it's
it's
here
here
phi
phi
is
is
a
a
function
function
of
of
XYZ,
XYZ,
right?
right?
Yeah.
So
So
when
when
you
you
take the
take the
derivative
derivative
with
with
respect to
respect to
x,
x,
indirectly you
indirectly
are
you are
saying
saying
in
in
the
the
direction
direction
of
of
x,
x,
how
how
much
much
is
is
the
the
change
change
in
in
phi.
phi.
Yeah. Yes.
Same
Same
with
with
y
y
and
and
same
same
with
with
z.
z.
That's
That's
how
how
it
it
is.
is.
So
So
this
this
effective
effective
would
would
be,
be
I
I
don't know
don't know
if
if
it's
it's
maximum
maximum
or
or
minimum,
minimum,
but
but
it
it
just
just
gives
gives
the.
the.
It
It
is
is
also
also
a
a
field.
field.
It's
It's
yeah.
yeah.
Maximum, I
Maximum, I
am
am
not
not
very
very
sure.
sure
Actually, I
actually. I
have to
need to
think
think
about
about
it.
it.
But
But
one
one
thing,
thing,
this
this
can,
can,
yeah,
yeah, true.
and
And
Actually,
one
one
more
more
they
thing.
thing,
give that. Yeah, what I learned that like looking into physical thing, that they said that if there is a mountain and we are climbing on the top, there could
Okay,
be multiple way, but the most
yes,
yes.
steeper way is
okay,
gradient.
Okay,
is
is
the
the
gradient.
gradient.
Okay,
Okay,
okay.
okay.
I
I
Yeah, but
understood.
that
understood.
is maths definition.
Yeah,
Yeah,
eh, the
the
concepts
concepts
won't
won't
change.
change.
I
I
think
think
if
if
you,
you,
it's
it's
like
like
effective.
effective.
These
These
are
are
like
like
individual
individual
components,
components,
but
but
if you
if you
add
add
up,
up,
then
then
it's
it's
like
like
in
in
x
x,
this
this
is
is
the
the
gradient,
gradient,
y
y,
this
this
is the
is the
gradient,
gradient,
and
and
if
if
you
you
get
get
the
the
vector
vector
components,
components,
effectively it
effectively it
would be
would be
like
like
you
you
are
are
adding
adding
those
those
gradient,
gradient,
and
and
I'm
I'm
guessing
guessing
you will
you'll
get
get
the
the
more
more
wherever
wherever
the
the
steepest
steepest
direction
direction
is.
is.
It's
It's
gradient
gradient
is
is
a
a
sum
sum
of
of
all
all
these
these
directions,
directions,
right?
right? So let's say
you
you
have
have
some
some
like if
if
we
we
just
just
take
take
2,
two,
and
and
like
like
in
in
x
its
direction
direction
this
this
is
is
dou
dou
phi
phi
by
by
dou
dou
x,
x,
and
and
y,
y,
let's
let's
say
say
this
this
is
is
dou
dou
phi
phi
by
by
dou
dou
y.
y.
Okay,
Okay.
so
So
if you
if
are
you are
adding,
adding,
it's
it's
like
like
you
you
are
are
you'll
you'll
get
get
some
some
this
this
effective
effective
1.
one.
Yeah, and it is the steeple, like it is more like
Yeah,
Yeah.
the maximum change, kind of maximum change.
yes,
Yes.
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 Maybe
Maybe
that's
that's
what
what
they
they
were
were
trying
trying
to
to
say.
say.
And
And
if you
if you
have
have
z,
Z,
you'll
you'll
Yeah,
even
and
add
actually,
that.
yeah, even actually, the resultant of these two, del phi by del x and del phi by del y, is the maximum. Actually, it is more than both of individual.
yeah,
Yeah,
it's
it's
more
more
than
than
both
both
of
of
this.
this.
True,
True,
that's
that's
true.
true.
Yeah.
Yeah.
Yeah, that's why it is steeper. Okay, yeah, understood. Okay, thank you. That
Yeah,
is
Yeah,
probably
probably
just
just
yeah.
yeah.
So
So
similarly,
similarly,
if
if
there
there
is
is
some
some
vector
vector
u,
u,
then
then
in
in
this
this
case
case
u
u
of
of
x y z,
xyz,
like
like
it's a
it's a
function
function
of
of
this
this
field,
field,
and
and
you will
you will
have
have
component
component
u1
u1
I
I
cap
cap
plus,
plus,
let's
let's
say,
say
u2
u2
j
j
cap
cap
plus
plus
u3
u3
j
j
cap,
cap,
or
or
something
something
like
like
u1
u1
u2
u2
u3,
u3,
like a
like a
displacement
displacement
or
or
velocity.
velocity.
Then
Then
if
if
you
you
have
have
you
you
want to
want to
perform
perform
gradient
gradient
on
on
this,
this,
you
you
what
what
will
will
happen
happen
is
is
it
it
will
will
become
become
something
something
like
like
dou
dou
u
u
1
1
by
by
dou
dou
x,
x,
dou
dou
u
u
1
1
by
by
uh,
uh, dou
dou
y
dou
dou
u
u
1
1
by
by
dou
dou
z.
z.
Same,
Same,
you
you
will
will
get a
get a
tensor.
tensor.
It's
It's
like
like
individually
individually
each
each
component
component
you
you
are
are
finding
finding
out
out
what's
what's
the
the
like
like
gradient
gradient
in
in
the
the
respect.
respect.
I think when we do this gradient, we will get del u1 by del x plus del u2 by del y, because like we are taking dot product, so I multiplied and then j j
Mm,
multiplied.
No,
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 it's
it's
not
not
dot
dot
prod.
product.
You
You
are
are
thinking
thinking
it's
it's
just
just
del
del
times
times
u.
u.
So
So
when
when
you
you
take the
take the
gradient
gradient
of
of a
vector,
vector,
you
you
will
will
get
get
like
like
second
second
order
order
tensor.
tensor.
So
So
okay,
okay,
it's
it's
like
like
same
same
way.
way.
It's
It's
like
like
individually
individually
you are
you are
seeing
seeing
like
like
first
first
component
component
of
of
u.
u.
How
How
is
is
it
it
like how
how
its
its
derivative
derivative
is
is
in
in
x
x
direction
direction
y
y
z,
z,
and
and
then
then
second
second
component
component
x
x
y
y
z,
z,
something
something
like
like
that.
that.
You
You
don't
don't
want
want
to
to
combine
combine
all
all
of
of
them.
them.
It's
It's
like
like
you will
you will
get
get
third
third
order
order
sorry, second
second
order
order
tensor.
tensor.
So
So
whenever
whenever
it's
it's
like
like
when
when
scalar
scalar
is
is
something
something
like
like
tensor
tensor
of
of
order
order
0,
0,
and
and
vector
vector
is
is
like
like
tensor
tensor
of
of
order
order
1,
1,
and
and
then
then
it's
it's
like
like
stress, all
all
those
those
are
are
stress
stress
and
and
strain
strain
are
as
second
second
order
order
tensors.
tensors.
When
When
you
you
apply
apply
gradient
gradient
to
to
this
this
fields,
fields,
it
it
will
will
increase
increase
the
the
order
order
of
of
tensor
tensor
by
by
1.
1.
So
So
when
when
you
you
apply
apply
gradient
gradient
on
on
scalar,
scalar,
you
you
will
will
get
get
first
first
order
order
tensor,
tensor,
that
that
is
is
vector,
vector,
and
and
then
then
tensor,
tensor,
something
something
like
like
this.
this.
So
So
it's
it's
like
like
basically
basically
in
in
all
all
those
those
direction
direction
how
how
each
each
component
component
is
is
changing, you
changing, you
want to
want to
see.
see.
That's
That's
basically
basically
the
the
gradient.
gradient.
Just a minute, I'm trying to write it.
Yeah,
Yeah, yeah.
I
I
can
can
share
share
these
these
things.
things.
Okay,
Okay.
okay.
So
It's
by
It's
something
something
gradient,
like
we are seeing
it's
it's
something
individually
something
it
it
would
would
look
changes.
look
like
like
dou
dou
by
by
dou
dou
x,
x,
dou
dou
by
by
dou
dou
y,
y,
dou
dou
by
by
dou
dou
z
z
times
times
it
it
would be
would be
like
like
u1,
u1,
u2,
u2,
u3.
u3.
So
So
if
if
you
you
multiply
multiply
it,
it,
you
you
will
will
get
get
it.
it. Then
Then okay,
okay,
I
I
think
think
I
I
wrote it
wrote
in
it in
wrong
wrong
order.
order.
It
It
should be
should be
transpose
transpose
of
of
this.
this.
Okay,
Okay,
it
it
would
would
look
look
like
like
this,
this,
like
like
this
this
gradient
gradient
operating
operating
on.
on.
Uh, but this is this is a vector. U is a vector. and it is
Yes.
of order 1. It is of order 1. Or like
Yes,
you have said
vector
that.
u is called tensor of order one.
Yeah,
It's
It's
like
like
tensor
basically
basically,
order 1.
yeah.
then
Then
But
you
you
are
are,
when we apply gradient,
yeah,
yeah,
you
you
are
are
getting
getting
tensor
tensor
of
of
order
order
two.
two.
That
That
is
is
like a
like a
matrix
matrix
you
you
will
will
get.
get.
You
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 can
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 probably
probably
know
know,
do.
you already
already
know
know
like
like
this
this
strain
strain
is
is
del
del
times
times
u.
u.
So
So
u
u
is a
is a
vector
vector
and
and
it's
it's
you are
you are
acting
acting
gradient
gradient
on
on
u.
u.
So
So
you are
you are
getting a
getting a
second
second
order
order
tensor
tensor
strain.
strain.
Okay, like how it is second order? Like we have three x, y, z.
No,
No,
it's
it's
when
when
I
I
say
say
second
second
order,
order,
it
it
means
means
we
we
will
will
have
have
like
like
here
here
we
we
just
just
have
have
one
one
column,
column,
but
but
here
here
when we
when we
write
write
we
we
will
will
have
have
one
one
row
row
and
and
one
one
column.
column.
Like
Like
that's
that's
how
how
it's
it's
like
like
second column,
column,
second
second
order.
order.
So
So
Okay,
yeah,
yeah,
this
this
is
is
matrix
matrix
notation.
notation.
This thing, it's
It's
actually
actually
even
even
if
if
you
you
want
want
to
to
write
write
it
it
in
in
this
this
index
index
notation.
notation.
Actually,
Actually,
what
what
happens
happens
is
is
there's
there's
something
something
called
called
we
we
like
like
this
this
all
all
these
these
matrix
matrix
terms.
terms.
If
If
you
you
will
will
write
write
it
it
as
as
dou
dou
u1
u1
by
by
dou
dou
x
x,
I
I
cross
cross
I
I
plus
plus
something
something
like
like
that
that
you
you
will
will
write.
write.
So
So
this
this
is
is
this
this
gives
gives
the
the
order
order
as
as
second
second
order.
order.
But
But
better
better
you
you
can
can
simply
simply
stick
stick
with
with
matrices
matrices
instead
instead
of
of
doing
doing
IJK.
IJK.
So
So
gradient
gradient
basically
basically
each
each
component
component
of the
of the
function
function
you
you
will
will
see
see
in
in
each
each
corresponding
corresponding
direction
direction
how
how
it's
it's
gonna
gonna
change,
change,
like
like
what
what
will
will
be
be
the
the
change.
change.
So
So
is it
is it
fair?
fair?
yeah.
Yeah,
Can I ask one more thing in
Yeah,
yeah,
between?
yeah,
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 no
no
problem.
problem.
Yeah, it is further more basic. Actually,
Sir,
Small.
small.
this is about like this is more basic thing.
Okay,
Okay,
Like
okay.
okay.
yeah. Actually, while even while
I'll
taking the notes, like it is not a bad idea. Like to write, like people suggest that like you share, that is okay, but better to
Oh,
write
okay.
okay.
like
Okay,
Okay,
while
while
I'm
I'm
saying
saying
whatever
whatever
I'm
I'm
saying, I
saying, I
should
should
write
write
something
something
like
like
that.
that.
uh,
Yeah,
Yeah,
okay,
okay,
I'm
I'm
not
not
good
good
at
at
note
note
skipping.
skipping.
I'll
I'll
try
try
my
my
best.
best.
even I
And
study, there are method like Cornell methods for taking notes, so they suggest to like better to write it. So that's why
Uh,
I just
true,
True, true.
confirm.
yeah,
Yeah,
true,
true,
but
but
I'm
I'm
just
just
very
very
bad
bad
at
at
it.
it.
Even
Even
I
I
don't
don't
prepare
prepare
any
any
like
like
specific
specific
notes
notes
for
for
the
the
class.
class.
I
I
just
just
see
see
and
and
keep in
keep
my
in my
mind.
mind.
Okay,
Okay,
I'll
I'll
just
just
discuss
discuss
this,
this,
something
something
like
like
that.
that.
Okay,
Okay,
I'll
I'll
try.
try.
Okay, then how it help to revise, like while revising the concepts, how it help, like how you do while revising it.
Uh,
And
while
while
revising,
revising,
yeah,
yeah,
I
I
should
should
probably
probably
give.
give.
Till
Till
mostly
mostly
I
I
was
was
like
like
a
a
student,
student,
so
so
I
I
used to
used to
get
get
notes
notes
from
from
the
the
faculty
faculty
or
or
some
some
books
books
I
I
used to
used to
read.
read.
But
But
teaching
teaching
was
was
new to
new to
it,
it,
so
so
I
I
never
never
thought
thought
of about
about
it
it
this
this
from
from
this
this
side.
side.
Yeah.
Yeah,
Well,
hell, I
okay.
okay.
So
So
it's
it's
gradient
gradient
is
is
fine,
fine,
right?
right?
So
So
it
it
gives
gives
the
the
like
like
variation
variation
in
in
those
those
corresponding
corresponding
directions,
directions,
and
and
it
it
increases
increases
one
one
order
order
of
of
this
this
thing.
thing.
and then a divergence, it would be like divergence. First thing, it reduces the tensor order by one, and it won't act on scalars. Divergence, at least it acts on a vector. So when you say it is divergence, it's the dot product actually. So it would look like dou u1 by dou s plus dou u2 by dou y plus dou u3 by dou z. This is the like dot product, whatever you are saying. Okay,
Okay.
and it will give its scalar component. So
So
tensor
tensor
order
order
is
is
0.
0.
Something like it reduces by one order. And let's say you have applied divergence on stress, which is like second order. So
So
it
it
reduces
reduces
it to
it to
first
first
order.
order.
Something
Something
like
like
dou
dou
sigma
sigma
1
1
bar.
bar.
It's
It's
like
like
the
the
first
first
component,
component,
and
and
then
then
you
you
will
will
have
have
similarly
similarly
other
other
two.
two.
Okay,
Okay.
it's
It's
like
like
it
it
reduces
reduces
the
the
order
order
by
by
one.
one.
That's why
That's why
you
you
will
will
have
have
when
when
we
we
have
have
this,
this,
you
you
have
have
three
three
equations.
equations.
Tensor
Tensor
order,
order,
it
it
would
would
become
become
1
1
from
from
so
so
1
1
to
to
becomes
becomes
0
0
and
and
2
2
to
to
becomes
becomes
1.
1.
So
So
divergence,
divergence,
it's
it's
never
never
like
like
a
a
divergence
divergence
is
is
applied
applied
on
on
a
a
scalar.
scalar.
So
So
when
when
you
you
say
say
divergence,
divergence,
it's
it's
like
like
when you
when you
think
think
about
about
it a
it a
vector
vector
field,
field,
it's
it's
like
like
in
in
a
a
3D
3D
space.
space.
At
At
each
each
and
and
every
every
point,
point,
there
there
is
is
a
a
vector
vector
associated
associated
with
with
that
that
point.
point.
So
So
it's
it's
like
like
so
so
when you
when
are
you are
calculating
calculating
divergence
divergence
at
at
some
some
point,
point,
it's
it's
like
like
kind
kind
of
of
saying
saying
that
that
from
from
that
that
point
point
how
how
much
much
the specific
specific
quantity
quantity
is
is
coming
coming
out or
out or
going
going
inside
inside
through
through
that.
that.
Something
Something
like
like
that
that
is
is
the
the
divergence.
divergence.
Effectively,
Effectively,
what
what
it
it
means.
means.
It's
It's
effectively
effectively
says
says
about
about
the
the
quantity
quantity
of
of
that.
that.
Uh,
Uh,
it's
it's
like
like
coming
coming
out
out
or
or
going,
going
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 into
into
in the
in the
at
at
that
that
specific
specific
point.
point.
It's
It's
not
not
very
very
official
official
definitions.
definitions.
Better
Better
if
if
you
you
look
look
at
at
some
some
book
book
for
for
better
better
wording
wording
and
and
better
better
clarity.
clarity.
But
But
this
this
sense
sense
is
is
this
this
one
one
when you
when you
say
say
divergence.
divergence.
So
So
it's
it's
So,
something
something
like
like
if I take divergence,
yes,
yes,
yeah, please go ahead. Then I will.
yeah.
yeah.
So
So
it's
it's
something
something
like
like
let's say
let's say
you
you
have
have
fluid
fluid
flow,
flow,
flow
flow
rate,
rate,
and
and
there
there
is a
is a
field,
field,
right?
right?
A
A
flow
flow
rate,
rate,
fluid
fluid
velocity, it
velocity, it
has
has
some
some
field.
field.
So
So
when
when
you
you
do
do
something
something
like
like
del
del
dot
dot
q,
q,
we are
we are
saying
saying
something
something
like
like
how
how
much
much
fluid
fluid
is
is
coming
coming
out
out
from
from
that
that
point.
point.
And
And
let's
let's
say
say
if it
if it
is
is
positive,
positive,
implies
implies
something
something
like
like
fluid
fluid
is
is
coming
coming
out
out
from
from
that
that
point.
point.
And
And
let's
let's
say if
say
it
if it
is
is
negative,
negative,
it's
it's
like
like
fluid
fluid
is
is
going
going
in,
in,
something
something
like that.
like that.
And
And
magnitude
magnitude
gives
gives
how
how
much
much
like
like
quantity
quantity
of the
of the
fluid is
fluid is
coming
coming
out
off
or
or
something
something
like
like
that.
that.
So
So
if
if
divergence
divergence
of
of
this
this
is
is
high,
high,
it's
it's
like
like
more
more
large
large
volume of
volume of
fluid is
fluid is
coming out,
coming out,
and
and
if
if
it's
it's
very
very
low,
low,
it's
it's
relatively
relatively
low,
low,
something
something
like
like
that.
that.
You
You
get
get
the
the
concept,
concept,
right?
right?
Yeah, but if there is a continuous flow, uh, like there
Yes.
yes, please if you make a like rectangle and from one end fluid is entering and from the other end fluid is leaving.
Yes.
Yeah, from other end it is leaving, then somewhere in between the middle point the
Yes.
divergence is zero.
Yeah, if it is equally coming and equally going, then divergence will be zero. You might have studied like for incompressible fluids, something like divergence of velocity is zero, something like that. Like this, you might have studied, right? So
Okay. So it only told
it's
about the source and the sink, nothing else.
okay. Okay. Generally, in incompressible, when we say it's like the density of the fluid doesn't change. So if you take a specific volume, whatever fluid comes in will definitely go out. So it's
Yeah.
definite. Basically, the divergence will be like zero. So if it's
Okay.
uh, yeah, let's say somewhere here density is changing and it's compressible, something like that, then it would divergence changes, or else let's say there is some uh, yeah, something like that. If it's equal coming and equally
Yeah,
going
if
out,
if
then
some
it's yeah.
if some mass is getting stored, then divergence is not zero, right?
Yes, yes.
Okay.
Same thing you can think about heat flux, something like it's like when you do the divergence of heat flux, it's something like how much heat is coming out, something like that you can think. So depending on this quantity which you are applying divergence on, correspondingly you will have some other quantity, it's corresponding scalar quantity which you can talk about.
So if in a heat flux, if
Yes, yes, yes.
in a
In a
heat
heat
flux, if it if the condition is steady, then
yes.
there also divergence of flux is zero.
Not necessary. When you say it's steady, it just means that it doesn't change with time. But these are with
That is
respect to
only
space.
yeah, but
There,
the in heat in specifically in heat, the steady state comes only when temperature doesn't change at that particular. That is only possible if the heat coming in will go up.
no, no. It's like when you say steady state, it means temperature doesn't change with time. It can change with space. Something like that you can
But it
think.
remain
Yeah, it remains constant with time. So something like this temperature is present, and it's gradually, slowly, like field is varying from 10 to 5, left to right. But it is constant with time, then it is called steady state. But when you say in space, it's it can have change.
that I understand. Like if you
Okay.
can make like from 10, 10, 8 or 9 to up to
Yeah.
5 something.
Yeah.
But when a heat flux is entering from one point
Yes.
and to at a particular point, if 10 is need to be maintained with
Yes.
time,
Okay.
then it is a necessary condition that it should the heat flux it is coming out should must go to the 10 to the
Oh,
9.
okay. I understood. What you are saying is like if for a, if you want to maintain the temperature, then whatever the flux is coming in should go out, kind of thing. Yeah,
Yeah,
that makes
so
sense. Makes sense. True.
that's why divergence is zero, like if it is steady.
Yeah, makes sense. True.
Mhm.
Yeah. So here, when you apply it on stress, you will get something called traction vector. It's same as the force. That's why you will have when you you have this definition like, sorry, this is not traction vector, but it's equivalent to force. Like when you have divergence of fluid velocity, you have amount of fluid. So when you have divergence of stress, it's like uh, some kind of force you can think about it.
Oh, this I don't get. Please, like you for fluid also you told that what when you take divergence of this, then what it get? What you get?
Uh, when you have divergence of fluid velocity, it's the amount of fluid quantity, like amount of fluid, volume of
Volume.
fluid you can think.
Like how we get like divergence of velocity will give quantity of fluid.
Yeah, so it's like Q is probably, let's say, meters per second, and
Please take it U. That will be convenient.
sorry,
Please take it U. Q like
U.
meter per second. U meter per second. Yeah.
U is velocity meters per second, and then if you apply divergence of Q, it would be per second. Okay, okay, it's not. Okay, we need to take flat side. This velocity per unit area is no.
Like for is even for stresses like even it stresses per unit area. So like
Stress is like force per unit area.
yeah. So here also if we take divergence, like how it will give it will be when we take
Divergence of stress would be like force per, yeah, sorry, it's force per unit volume. It's not direct force, it's equivalent force, something like that. Force per unit volume you will get. And I think similarly here also it's like volume of fluid per unit volume kind of thing you can think maybe.
okay.
It's you'll get force per unit volume.
Okay. Okay. Yeah.
Yeah. So it's like that's why if you do something with this with the integral, then you can get something like for total volume.
Okay, like the divergence of stress, if we integrate it with respect to volume, then we will get
Uh, yeah,
force
it's force per unit volume is the if you integrate this one.
so like one thing we are
I,
looking it
I
into.
don't think we do this, but generally, if you generally get these quantities, but if you do the integral accordingly, you will get the like something like it's divergence of some quantity is present, and if we are integrating it volume, it's like this is for a specific point, and if you do it for the whole region, it would do like effective like for a point, it's like coming out of or going in will do divergence of that some quantity at that point. But if you, let's say, you want to see for some bit volume how much is coming out or going in, then you do this one, integrate the divergence of u over the whole volume, because divergence just gives for a point, but let's say you are interested in the whole volume effectively, how much is coming inside and how much of quantity is going outside of that whole volume, then you do this one.
Now it really makes sense like towards the FEM equations also. That's why we are going for.
Yes,
Yeah,
you
you
like
like
this
this
basic
basic
concepts if
concepts. If
you
you
understand,
understand,
then
then
it
it
becomes
becomes
easier to
easier to
understand
understand
those
those
things
things
as
as
well.
well.
Yeah,
Yeah,
there's
there's
this
this
Gauss
gross
divergence
divergence
theorem
theorem
as well,
as well,
right?
right?
Maybe
Maybe
I'll
I'll just
go
go
into
into
that
that
as I
as I
came
came
here. I
here.
will
I will
tell
tell
what
what
that
that
generally
generally
tells it. Tells
tells
us
us.
Gauss
Gross
divergence
divergence
theorem.
theorem.
It's
It's
basically
basically
converts
converts
from
from
volume
volume
integral
integral
to
to
something
something
like
like
to
to
the
the
boundary
boundary
integral,
integral,
surface
surface
integral,
integral,
something
something
like
like
this,
this,
right?
right?
Yes.
So
So
what
what
this
this
means
means
is
is
just now
just
I
now I
told
told
it's
it's
just
just
tells the
tells the
amount
amount
of
of
fluid
fluid
coming
coming
out
out
of
of
this
this
whole
whole
volume,
volume,
right?
right?
Yeah.
And
And
specifically
specifically
same
same
even
even
here.
here.
If you
If you
see
see
u
u
dot
dot
n,
n,
u
u
is
is
some
some
vector,
vector,
and
and
this
this
n
n
would be
would be
surface
surface
normal.
normal.
Okay.
Okay.
So
So
when
when
you
you
do
do
u
u
naught
naught
n,
n,
u
u
dot
dot
n,
n,
we are
we are
effectively
effectively
getting the
getting the
component
component
of
of
this
this
variable
variable
in
in
this
this
direction.
direction.
Okay,
Okay,
along
along
this
this
surface.
surface.
And
And
when you
when you
integrate
integrate
this
this
over
over
this
this
surface,
surface,
you will
you will
get
get
how
how
much of
much
the
of the
quantity
quantity
is
is
leaving
leaving
or
or
coming in
coming in
from
from
this
this
surface.
surface.
Empirical gave
So
So
it's
it's
like
like
u
u
is
is
present at
present at
all
all
these
these
points.
points.
So
So
let's
let's
say
say
at
at
this
this
point,
point,
some
some
random
random
u
u
is
is
like
like
this.
this.
So
So
if you
if you
divide the
divide the
components, it
components, it
would
would
be
be
like
like
this
this
and
and
this.
this.
So
So
only the
only the
normal
normal
vectors
vectors
would
would
do
do
tell
tell
about the
about the
quantity
quantity
that is
that is
going
going
out
out
or
or
in.
in.
This
This
tangential, it
tangential, it
doesn't
doesn't
tell
tell
you
you
about
about
the
the
quantity
quantity
going
going
out,
out,
right?
right?
They
They
just
just
still
still
stay
stay
within
within
the
the
volume.
volume.
So to
So to
get
get
this
this
normal
normal
vector,
vector,
you'll
you'll
do
do
this
this
u
u
dot
dot
n,
n,
and
and
it's
it's
per
per
unit
unit
surface.
surface.
Then you
Then you
will
will
do it
do it
integrate it
integrate it
over
over
the
the
whole
whole
surface.
surface.
So
So
basically,
basically,
both
both
of
of
them are
them are
saying
saying,
yeah. So only that's why we are only taking this vector which is normal, right?
uh,
uh,
it's
it's
u
u
is
is
vector,
vector,
n
n
is
is
the
the
normal to
normal
the
to the
surface,
surface,
which
which
we
we
are
are
doing.
doing.
So
So
sometimes you
sometimes you
might
might
see
see
this
this
as
as
something
something
like
like
u
u
dot
dot
ds.
ds.
So u
In
dot
In
this
this
n
case,
will
case,
just a minute.
yeah.
U dot n will only give this vertical component which is coming
no,
out.
no,
No, no,
it's
it's
like
like
n
n
changes
changes
with
with
s.
s.
If
If
at
at
this
this
point
point
n is
n is
this.
this,
Let's say
let's
you
say you
have
have
arbitrary
arbitrary
surface.
surface.
So
So
at this
at this
point
point
n
n
would
would
be
be
to
to
normal to
normal to
this.
this.
At
At
this
this
point it
point
would
it
be
would be
normal to
normal to
this.
this.
Okay.
Okay.
Okay. So u
It's
is
It's
not
not
like
not
like
sorry
sorry,
you.
you.
u is not like not normal. When we multiply it with n, we get that component in the
Yes,
Yes,
direction.
when you
when you
when you
when you
take the
take the
dot
dot
product, you
product,
will
you will
get
get
a component
component
along
along
this
this
normal.
normal.
Okay. When just a minute. Okay. Yeah.
Yeah.
So
So
this
this
is
is
basically
basically
whole
whole
idea of
idea of
Gauss
gross
divergence
divergence
theorem.
theorem.
But
But
if you think in a
in
physical
physical
sense,
sense,
this is
this is
the
the
whole
whole
idea.
idea.
But
But
the we
we
use it
use it
this
this
thing
thing
while
while
we are
we are
doing
doing
for
for
weak
weak
form
form
to
to
shift
shift
the
the
reduce the
reduce the
order of
order of
derivative.
derivative.
Yeah,
But
and
But
this is not useful for 1D. Like 1D, we by integration by
no,
part we
no,
directly get.
1D
one day
it's
it's
yeah,
yeah, one
1D
day
this
this
is
is
more
more
to do
to
with
do with
2D
2D
and
and
3D.
3D.
1D
One day
it's
it's
normal
normal
derivative.
derivative.
It's
It's
like
like
normal
normal
UV
UV
integral
integral
rule
rule
kind of
kind of
thing.
thing you can say.
Yeah.
So when
when
you
you
do
do
1D,
1D,
even
even
there,
there,
first
first
thing
thing
would be
would be
something
something
like
like
uh,
uh,
this one
this one
is
is
like
like
derivative
derivative
along
along
all
all
these
these
points.
points.
The
The
contradict
contradict
side
side
would
would
be
be
something
something
like
like
take
take
the
the
value
value
at
at
this
this
point
point
and
and
take the
take the
derivative
derivative
at
at
this
this
point,
point,
and then
and
you
then
are
you are
just
just
saying
saying
the
the
difference
difference
of
of
this.
this.
Just wait, wait.
Right?
Right?
So there is
So
So
it's
it's
like
like
even
even
here,
here
it's
it's
like
like
the
the
derivative
derivative
of
of
along
along
this
this
region,
region,
you are
you are
integrating
integrating
it
it
over the
over the
region
region
to
to
get
get
how
how
much
much
effective
effective
quantity is
quantity is
going
going
out or
out or
coming
coming
in.
in.
So
So
it's
it's
nothing
nothing
but
but
the
the
boundaries
boundaries
of
of
this
this
region
region
is
is
just
just
this
this
point
point
and
and
this
this
point.
point.
So you
So you
can
can
just
just
subtract it,
subtract it,
u2
u2
minus
minus
u1
u1
kind of
kind of
thing.
thing.
Right.
Right.
It's
It's
nothing
nothing
but
but
basically
basically
solving the
solving the
integral
integral
itself.
itself.
Integral of
Integral
dou
of
u
dou
by
u by
dou
dou
x
x
dx
dx
is
is
nothing but
nothing but
u2
u2
minus
minus
u1.
u1.
Right.
Right?
right.
Okay.
Okay.
So
So
this
this
is
is
if
if
you
you
expand
expand
this
this
concept to
concept to
2D,
2D,
this is
this is
what you
what
will
you will
get,
get,
2D or
2D or
3D.
3D.
Actually,
Actually,
this is
this is
for
for
3D.
3D.
In
In
2D,
2D,
it's
it's
from
from
surface to
surface to
line
line
integral you
integral
will
you will
get.
get.
Yeah.
Yeah.
Yeah, yeah. That is what I'm looking into the equation like for 2D like in this way.
Actually,
Actually,
this
this
is
is
3D,
3D,
not
not
2D.
2D.
It's
It's
I'm
I'm
showing
showing
it.
it.
There you
There
will
you will
get
get
from
from
surface to
surface to
line
line
integral.
integral.
Yeah, and like here, there in that we use two equation like one in x direction, one in y direction, because there we are independently calculating these things, one in x, one in y.
Uh,
Uh,
can you
can you
say the
say the
expression?
expression?
The expression is like integral domain integral like
Okay.
Okay.
uh, the, this integral is in that domain like in that symbol we make below the domain.
This one.
This one.
No, no, no. Domain that omega integral omega
Okay,
domain.
Omega.
Omega.
Okay.
Okay.
Yeah, del upon del x, and then in bracket w f1, and then it is closed. Now dx dy, no
Okay.
Okay.
dx dy. It is equals to boundary integral w f1 nx ds, nx ds, and in the second part ds,
Yeah.
Yeah.
Okay.
and the second part is like instead of del upon del x we have del upon del y, so in the right hand side it
Yeah,
Yeah,
become
I
I
did.
did.
like f2, the quantity is f2, anyway doesn't matter.
Yeah.
Yeah.
Yeah,
Yeah.
so here
Okay.
n vector we have also taking component of n vector like nf and ny.
Yeah,
Yeah,
this is
this is
also
also
it's
it's
component
component
only.
only.
Like
Like
basically,
basically,
yeah,
yeah,
it's
it's
yeah,
yeah,
true.
true.
It's
It's
something
something
like
like
if
if
instead of
instead of
taking
taking
normal, you
normal,
are
you are
writing
writing
in
in
terms
terms
of
of
x
x
and
and
y.
y.
Yeah,
Like
and
let's
Let's
say
to
say
here,
here
this
this
is
is
n
n
normal,
normal,
but
but
instead of
instead of
writing in
writing in
terms of
terms of
normal, you
normal,
are
you are
just
just
writing
writing
in
in
terms of
terms of
nx
nx
and
and
ny.
ny.
That's
yeah,
That's
all.
it.
yes, yes,
That's it.
That's it.
Nothing
Nothing
different.
different.
So
So
here,
here
instead of
instead of
writing
writing
directly f,
directly
we are
f, you are
taking
taking
f1 and
f1 and
f2.
f2.
okay, and we can write it in divergence form or we can write it in this form what I have told, like, what I make you write
Yeah,
Yeah,
this form.
both are
both are
same.
same.
Uh,
Uh,
it's
it's
just
just
better
better
to
to
use
use
this
this
one
one
because
because
it's
it's
more
more
compact.
compact.
It's
It's
like
like
you
you
will
will
understand it
understand it
once you
once you
understand the
understand the
concept.
concept.
You
You
won't
won't
find
find
it
it
difficult to
difficult to
use
use
in
in
this
this
directly.
directly.
Okay.
It's more compact form of better way
But
of
here,
writing.
yeah, but in divergence we understand that thing. Like say if WF1 is some quantity,
Yes.
Yes.
it's we are taking its difference, like its change in x direction,
Yes.
Yes.
and then in t when we are in whole domain we are collecting our change,
Yes.
so
Yes.
it is like coming out from that domain.
Yes.
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 Basically.
Decimal.
Okay. So that's we look into the boundaries, like how it is getting the boundaries in the right hand side,
Yes.
Yes.
right?
Yes.
Yes.
I get the physical idea thing. Yeah,
Yes.
Yeah.
please
Yes.
carry on.
These
These
are
are
especially
especially
mainly
mainly
for
for
divergence
divergence
and
and
gradient.
gradient.
These are
These are
generalized
generalized
things
things
like
like
it
it
will
will
work
work
on
on
scalar,
scalar,
vector,
vector,
tensor,
tensor,
anything.
anything.
Divergence
Divergence
works
works
from
from
like
like
first
first
order
order
onwards it
onwards
will
it
work.
will work.
Divergence
Divergence
it's
it's
like
like
increases
increases
and
and
this
this
one
one
it's
it's
decreases,
decreases,
it's
it's
fine.
fine.
All
All
these
these
things
things
are
are
it's
it's
fine.
fine.
Then
Then
comes
comes
curl.
curl.
Curl
Curl
is
is
specifically
specifically
for
for
only
only
like
like
3D
3D
case
case
or
or
2D
2D
case.
case.
It's
It's
like
like
you are
you are
doing the
doing the
cross
cross
product
product
between
between
the
the
derivative
derivative
and
and
this
this
one,
one,
something
something
like
like
this.
this.
This
This
probably
probably
you
you
know
know
something
something
like
like
this.
this.
So
So
when you
when you
take the
take the
cross
cross
product,
product,
let's say
let's
at
say
a
at a
point,
point,
something
something
like
like
let's say
let's say
this
this
is
is
your
your
u,
u,
and
and
you are
you are
doing
doing
it
it
with
with
some
some
like
like
gradient
gradient
cross
cross
product.
product.
It's
It's
something
something
like
like
you are
you are
you will
you will
get
get
around this
around this
point
point
how
how
much
much
it's
it's
rotating
rotating
this
this
thing.
thing.
Uh, Divergence
Divergence
curl
curl
it
it
gives the
gives the
amount of
amount of
rotation.
rotation.
Divergence
Divergence
it's
it's
gives
gives
something
something
like at
like
a
at a
point
point uh,
how
how
much is
much is
coming
coming
out or
out or
coming
coming
in,
in,
something like
something
that.
like that.
Curl
Curl
says
says
about
about
the
the
rotation
rotation
around
around
that
that
point.
point.
Especially
Especially
in
in
solid
solid
mechanics, we
mechanics, we
don't
don't
come
come
across
across
curl
curl
that
that
much.
much.
But
But
yeah,
yeah,
I
I
don't
don't
have
have
nothing
nothing
much to
much to
tell
tell
about
about
this
this
curl.
curl.
If you
If
have
you
any
have any
doubts, you
doubts, you
can
can
ask.
ask.
Like this curl actually we use in like in fluid mechanics.
Yes,
Yes,
fluid
fluid
mechanics
mechanics
especially.
especially.
Yeah,
Yeah,
it's
it's
like
like
something like
like
irrotational
irrotational
fluid.
fluid
You
you
probably
probably
might
might
have
have
heard,
heard,
Yeah,
right?
right?
Where
Where
we
we
say
say
that
that
del
del
cross
cross
U
u
is
is
zero,
zero,
right?
right?
yeah, yeah.
Basically,
Basically,
that's what
that's
we are
what we are
saying.
saying.
Irrotational
Irrotational
means it
means it
doesn't
doesn't
have
have
any
any
kinds of
kinds of
rotation
rotation
flow.
flow.
So
So
what we
what
are
we are
saying
saying
is
is
this
this
swirling
swirling
or
or
rotating
rotating
about a
about a
point is
point is
zero
zero
everywhere.
everywhere.
So
So
everywhere
everywhere
it's
it's
just
just
straightforward or
straightforward or
something
something
like
like
that.
that.
Okay, and for a flux also can use curl. Curl is not used for flux.
Yeah, you
Yeah,
can.
you can.
It's
It's
useful.
useful.
Yeah,
Yeah.
it
It
also
also
basically
basically
tells the
tells the
same
same
velocity or
velocity or
flux are
flux are
like
like
uh, equivalent
equivalent
terms.
terms.
Both of
Both
them
of them
talk
talk
about the
about the
amount of
amount of
fluid
fluid
only.
only.
Okay.
Yeah.
Yeah.
Like what just one thing, like we make generally a circle kind of thing, and through it some lines are passing, and for that we use curl sometime. I don't know.
Uh,
Uh,
okay,
okay,
something
something
like
like
this
this
integral. Are
integral.
you
Are you
saying?
saying?
No, not integral. Generally make one circle,
Okay,
Okay,
and
and
through
then
and
it
then
some lines are passing.
okay,
okay,
Not like this, from inside to outside. Like,
okay,
okay,
just random lines from one start at one point from the left hand side of the circle and goes to the right hand side. No.
sorry.
sorry,
Uh,
I don't get
Just
it.
please just make some big lines, right?
like
Like
this.
this.
Yeah.
Okay,
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 And
okay,
they have some one direction, like in, let's say, in some right hand side.
okay,
okay,
Yeah. And along that circle we have some small components, like through it we want to find out how flux. Yeah, that's such kind of things. Like
Yeah,
Yeah.
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 We
We
use
use
curl
curl
like
like
similar
similar
to
to
divergence. If
divergence.
you
If you
do
do
this
this
curl
curl
over
over
this
this
whole
whole
surface,
surface,
you'll
you'll
get
get
the
the
whole
whole
rotation
rotation
kind of thing, kind of
kind of
thing.
thing.
okay,
Okay.
Okay.
Generally,
Generally,
this
this
starts
starts
about a
about a
specific
specific
point
point
like
like
curl.
curl.
But if
But
you
if you
want to
want to
find out
find out
kind of
kind of
overall
overall
surface,
surface,
then you
then you
do
do
this.
this.
okay.
Mm, yeah.
Yeah.
So
So
these are
these are
basically
basically
the
the
like
like
divergence,
divergence,
gradient,
gradient
and
and
curl.
curl.
In
In
FEM
FEM
point of
point
view,
of view,
mainly
mainly
you
you
use
use
this
this
cross
cross
divergence
divergence
theorem,
theorem,
so
so
that
that
when
when
you
you
see
see
this
this
cross
cross
divergence
divergence
theorem,
theorem,
mainly
mainly
not
not
just
just
the
the
volume
volume
to
to
surface,
surface,
you
you
can
can
see
see
that
that
derivative
derivative
is
is
become
become
also
also
becoming
becoming
one
one
order
order
less.
less.
So we
So we
want to
want to
exploit
exploit
that
that
factor
factor
when we
when
are
we are
using
using
FEM.
FEM.
So
So
when we
when we
have
have
one
one
order
order
less
less
derivative, we
derivative, we
can
can
take
take
one
one
order
order
less
less
approximation
approximation
function.
function.
And
And
also
also
this
this
term
term
kind
kind
of
of
gives
gives
the
the,
Can you please
uh,
repeat this thing?
maybe
maybe
I'll
I'll
take
state
one
one
example and
example
then
and
we
then we
can
can
see
see here
how,
how,
like
like
while
while
using
using
FEM,
FEM,
let's
let's
just
just
state
state
this
this
elasticity
elasticity
problem.
problem.
We
We
have
have
weight
it
like
like
multiplied by
multiplied by
weight.
weight.
So
So
this is
this is
how
how
it would
it would
look
look
like
like
just with
just with
multiplied by
multiplied by
weight,
weight
and then
and then
integral
integral
uh,
uh,
over the
over the
domain
domain
is
is
zero,
zero,
right?
right?
And
And
let's
let's
say
say
we
we
apply
apply
the
the
gauss
gauge
divergence
divergence
here.
here.
What
What
happens
happens
is
is
we
we
have
have
this
this
divergence
divergence
shift
shift
to
to
this
this
something
something
like
like
this. It
this it
would
would
come.
come.
Yeah.
Yeah.
But
But
here
here
it's
it's
like
like
same
same
UV
UV
kind of
kind of
rule,
rule,
but in
but in
1D
1D
when
when
you
you
do
do
this,
this,
this
this
component
component
would
would
be
be
something
something
like
like
U2
U2
minus
minus
like
like
U1
U1
kind of
kind of
thing,
thing,
but
but
here it
here
would
it would
be
be
more
more
towards
towards
this
this
term.
term
It's
is
similar
similar
to
to
whatever.
whatever.
It's not
It's not
directly
directly
cross
cross
divergence,
divergence,
but
but
UV
UV
rule
rule
only.
only,
But
but
we
we
get
get
this
this
component
component
similar
similar
to
one
1D
D
case.
case.
Mm,
Is it
Okay,
right?
this is
This
the
is the
one
one
you will
you'll
get.
get.
And one
And one
more
more
main
main
important
important
thing
thing
is
is
this
this
one
one
uh,
uh,
tells
tells
about
about
boundary
boundary
conditions
conditions
on
on
this
this
surface.
surface.
What are
What
the
are the
boundary
boundary
conditions?
conditions?
Sigma
Sigma
dot
dot
n is
n is
one
one
thing you
thing
can
you can
apply.
apply.
Sigma
Sigma
dot
dot
n is
n is
nothing
nothing
but the
but the
traction
traction
vector.
vector.
So
So
which
which
probably you
probably
will
you will
know,
know,
or
or
else
else
W.
W.
W
W
is like,
is like,
let's say
let's
if
say if
you
you
know
know
U
U
on
on
this
this
side,
side,
then
then
the
the
assumption of
assumption of
W is
W is
W will
W
be
will be
zero
zero
wherever
wherever
Q
Q
is
is
known.
known.
On the in the
In the
remaining
remaining
places, you
places, you
would
would
know
know
traction is
traction is
either
either
zero
zero
or
or
whatever
whatever
applied,
applied,
which is
which is
sigma
sigma
dot
dot
n.
n.
It's
It's
fine,
fine,
right?
right?
yeah, actually, this is the my doubt. Like we will come to it later. Like Before it, like I just want to ask, like we most of the time we use this direction cosine for n vector. Why?
Dot
Dot
n,
n.
this one.
This one.
Yeah, so a unit normal vector and direction cosine is they are same. They're like
Yes,
Yes,
they are
they are
same.
same.
Yeah, they
Yeah,
are
they are
same.
same.
It's
okay.
It's
just
just
Direction
when you
when you
say
say
normal
normal
and
and
when you
when you
say
say
unit
unit
normal,
normal,
basically you're
basically you're
talking
talking
about
about
direction
direction
cosines.
cosines.
okay. But direction cosine are only cos alpha, cos beta kind of things. But like
It's
It's
like
like
let's say
let's say
you
you
have
have
some
some
n,
n,
okay,
okay,
in this
in this
manner.
manner.
This is
This
n,
is
let's
n,
say.
let's say,
Okay,
okay.
so
So
what
what
nx would
nx would
be
be
magnitude is
magnitude
n,
is
let's
n,
say,
let's say,
and this is
and
the
this is the
director.
director.
So
So
nx would
nx would
be
be
magnitude
magnitude
times
times
cos
cos
theta, right?
theta, right?
This
And
one
this
would
one
be
would be
magnitude
magnitude
times
times
sine
sine
theta.
theta.
So if
So
you
if you
want to
want to
write
write
n,
n,
it would
it
be
would
like
be like
magnitude of
magnitude
n
of n
cos
cos
theta
theta
I
I
cap
cap
plus
plus
magnitude of
magnitude
n
of n
sine
sine
theta
theta
j cap.
j cap.
And let's
And
say
let's
when
say
you
when you
want
want
to,
to,
this is
this is
just
just
the
the
vector,
vector,
but you
but
want
you
to
want
have
to have
unit
unit
normal.
normal.
So if you
So if
want
you
to
want
have
to have
unit
unit
normal, you
normal,
need
you
to
need to
divide it
divide
by
it
the
by the
magnitude.
magnitude.
Okay,
Okay,
unit
unit
normal,
normal.
and
And
plus
plus
divided by
divided by
magnitude of
magnitude
n,
of
right?
n, right?
yeah.
So you
So
will
you
get
will get
cos
cos
theta I
theta
cap
I
plus
cap plus
sin theta
sin
I
theta j
cap,
cap,
which are
which are
nothing but the
nothing but the
direction
direction
cosines.
cosines.
So
So
basically
basically
both are
both are
same.
same.
When you
When
talk
you talk
about
about
unit
unit
normal,
normal,
Okay.
it
it
basically it's
basically it's
the
the
direction
direction
cosines.
cosines.
Yeah,
Yeah,
Interesting.
yeah,
yeah.
okay,
Okay.
No, no, yeah, like functional, like
yeah,
like
Yeah,
functional.
functional.
we can like that thing. This W and U is known. That is the last thing because that is again very more difficult. So better to go by like first tell about functional.
Okay, first
Okay, first
functional, then
functional,
we'll come
then
back to
come
this
back
one.
to this one.
Okay,
Yeah.
Okay.
so
So
let's talk
let's
about
talk about
functional.
functional.
Functional
Functional
is
is
nothing but
nothing but
it's like
it's like
you can
you
think
can
of
think
it
of
as
it as
function
function
of
of
functions.
functions.
Okay,
Okay.
so
So
let's see
let's
what
see
just
what just
function is
function is
first.
first.
Function, when you
Function,
say
when
a
you say a
function,
function,
it
it
means
means
let's
let's
say y
say y
is f
is
of
f of
x.
x.
Okay,
Okay.
Yeah.
so you
So
will
you
have
will
one
have one
input
input
which
which
is
is
like a
like a
variable,
variable
and
and
output will
output
also
will
be a
also be a
variable.
variable.
Something like
Something like
x to
x
y
to
you
y
are
you are
mapping.
mapped.
Okay,
Okay.
this is
This is
function.
function.
Okay,
Okay.
so in
So
our
in our
case,
case,
examples would
examples
be
would be
displacement is a
displacement is a
function of
function of
space.
space.
Okay,
Okay.
something like
Something
that,
like that.
right?
Right?
Uh,
Uh,
force may be a
Force may be a
function of
function
x.
of x.
Okay,
Okay.
something like that.
Something like that.
Let's say
Let's
there
say
is
there is
a
a
function of
function of
functional.
functional.
It
It
means it
means
is
it is
function of
function of
functions,
functions,
where u
where
is a
u is a
function in
function in
itself.
itself.
Okay,
Okay.
so
So
inputs of
inputs
a
of a
functional will
functional
be a
will be a
function.
function.
Inputs are
Inputs are
functions.
functions.
That's it.
That's it.
So
So
whenever we
whenever
talk
we talk
about this
about this
uh,
uh,
energy,
energy,
we say
we
it's a
say it's a
functional
functional
because
because
the
the
inputs of
inputs
this
of this
strain
strain
energy is
energy is
displacement, which
displacement,
is a
which is a
function.
function.
So when
So
we
when
talk
we
about
talk
strain
about
energy,
strain
we
energy, we
call it
call
as
it as
functional.
functional.
Fine.
Fine.
It's nothing but
Nothing but
Sigma,
sigma,
which is a
which is
function of
function
U,
of u,
strain, which is
strain,
a
which is a
function of
function
U,
of u
times T,
times t,
kind of thing.
kind of thing.
Yeah, right?
Yeah, right.
Yeah.
So
So
when you
when you
say
say
and this
and this
one
one
something like
something like
you are
you are
asked
asked
something like
something like
scalar
scalar
value,
valued,
vector
vector
value, right?
valued, right?
Functions.
Functions.
So
So
one thing
one
Like
is
thing is
yeah,
yeah,
just like if yeah, you write it.
yeah, yeah,
yeah,
I'll
yeah,
write
I'll
one
write
after
one
other.
after other.
Yeah,
Yeah.
Like if I write like integration of like some
yes,
Yes.
like function f
integral of
Integral of
function f.
function f.
f like then yeah, something like f dx or something dbj. Okay. So like what I thought till now that this integral of dv, that is a functional and we are putting fx in it.
No,
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 no.
that has
That has
nothing to
nothing
do.
to do.
That's
That's
functional
functional.
basically
Basically
means it
means it.
the
The
inputs
inputs
are
are
functions
functions
itself.
itself.
Like because
Normally, when
Normally, when
you
you
talk about
talk about
functions,
functions,
inputs are
inputs
just
are
a
just a
variables, right?
variables, right?
X or
X
mm,
Y.
or Y.
They are
They are
variables, not
variables, not
functions.
functions.
But when you
But
talk
when you
about
talk about
functional,
functional,
inputs are
inputs are
functions.
functions.
okay, but it is also told like if we are taking length of
Yes,
any
Yes.
curve,
yes.
Yes.
and
And
if
then
we like, and if we take area, then if we add two areas, then
Okay.
okay.
then it will give total area, so it is a functional. But if we take length of two curves and add it, it is not going to give the length of the new curve. So that is
I
I
don't
don't
understand, sir.
understand, sir.
oh,
What
that
is
is the
What?
oh, that is linear function. Sorry.
Oh,
Oh,
that's
that's
linear.
linear.
When you talk
When you
about
talk about
linearity,
linearity,
Okay.
linearity is
linearity
like
is like
when you
when you
have
have
inputs of a
inputs of a
function,
function,
and let's
and
say
let's
you
say
are
you are
multiplying it
multiplying
by a
it by a
constant, then
constant,
it's
then
like
it's like
uh,
uh,
this, and
this, and
then
then
let's say
let's
you
say
have
you
this.
have this.
It would
It
be
would be
these are like
these are like
linearity
linearity
conditions.
conditions.
If
If
function
function
satisfies these
satisfies
two
these two
conditions, then we
conditions, then
call
we
it
call it
linear.
linear.
Okay. And for that example is like that length
Yeah,
of
Yeah,
in that
in
case,
that
length,
case, length.
because area
Because
if you
area, if
do,
you do,
it's like
it's like
this
this
one
one
won't
won't
satisfy,
satisfy,
and even
and
this
even
one
this
won't
one won't
satisfy.
satisfy.
So
So
area is
area
not
is
not a
not a
linear
linear
function.
function.
okay. but but if there is something integral type of thing comes, like please write on
Yeah.
one thing, please.
Yeah, let's
Yeah, let's
say f
say
of
f of
x
x
is
is
integral x
integral x
square
square
d.
d
Uh,
uh,
Dx.
okay,
okay.
yeah,
Yeah, in that, in this, what is function? If fx is a functional, right?
it's a
It's a
function only
function only
because x
because
is,
x is
maybe you
maybe
can
you
think,
can
let's
think, let's
say
say
here
here
u,
u,
and you
and
say
you
u
say
is
u
equal
is
to
equal
x
to x
square,
square,
and
and
function is
function
f
is
of
f
u,
of u,
then
then
it is
it is
called
called
functional.
functional.
Get it?
Get it?
Yes, yes.
So if you
So
want
if
to
you
write
want
it
to
as a
write it as a
function,
function,
this would
this would
be
be
f of
f
x is
of x
equal to
is equal to
integral x
integral x
square
square
dx.
dx.
Okay. Yeah, so when we are writing like s is equals to here under root of x 1 plus du by dx, then it is okay, okay. Yeah, so we can like sometimes write a function in the form of functional.
Function in the
Function
form
in the
of
form of
functional, yeah,
function,
you
yeah,
can.
you can. uh,
convert it one
convert
to
it one
other.
to other.
The
The
problem is
problem is
when we are
when we are
solving for
solving for
this,
this,
we don't
we
know
don't
what
know what
exactly this
exactly
is,
this
right?
is, right?
Yeah.
That's what
That's
we
what
want
we
to
want to
find out.
find out.
So
So
we want to
we want to
find out
find
U
out
of
U
x,
of
right?
x, right?
Unknown
Unknown
in
in
general.
general.
So we
So
keep
we
them
keep
as
them
it is.
as
We
it is.
cannot
We cannot
take
take
arbitrarily some
arbitrarily some
value,
value,
some
some
function, and
function,
then
and
keep
then
it, right?
keep
We
it, right?
want
We
to
want to
find the
find the
function
function
itself.
itself.
So we
So we
cannot
cannot
go
go
in these
in these
cases.
cases.
Yeah.
It cannot
It
be
cannot be
converted to
converted to
function, right?
function, right?
So in that
So in
case,
that
we
case, we
just deal
just
with
deal with
keeping it as
keeping
a
it as a
functional only.
functional
We'll
only.
just
We'll
deal it
just deal it
with it.
with it.
And like just write down, just can you please write down one thing? Like
Yeah.
S
Yeah.
is equals to integral xa to xp, xa to xp, under root 1 plus du by dx whole square, du by dx square. This complete is under root
Okay, okay.
Okay, okay.
and dot ds. No, it's okay.
Oh,
You
okay.
Oh,
can,
The
okay.
square
This
is
square
there,
is
but
there, but
okay.
okay.
yeah, dot ds, dx.
Okay.
Okay.
Like it is if some graph is plotted between u and x, please,
Okay.
if some, please draw the
U is a
U
point.
is a
function of
function
x,
of
you are
x, you
saying.
are saying.
Yeah,
Yeah.
function of x, and some graph is
Yeah.
taken, then this ds is, this s is the length of that curve. Like
Yes.
if
Yes.
so,
Something like
Something like
yeah, just one.
let's.
so. If
So
it's
if it's
x,
it's,
then
then
this is
this
u
is
of
u
x.
of x.
Then
Then
s would
s
be
would
the
be
length
the
of
length of
this.
this.
Yeah,
Yeah.
and so and the, now u could be any function like ax plus b or
Yeah.
whatever.
Let's
Yeah.
say
Let's
if
say
it's
if
like
it's
this,
like this,
it would be
it would be
different length.
different
Yeah.
length. Yeah.
Yeah, so now this s is functional, right?
Yes.
Yes.
Okay, but how we can say it is function of, it is functional of what? Like
Uh,
we
Here,
Here,
s is
S is
functional of
functional of
u,
U.
okay,
because it
Because it
depends on
depends on
input is
input
u,
is U,
not
not
x.
X.
Let's say
Let's say
I won't
I
tell you
won't tell
what
you
is
what
u
is
of
U
x
of
is,
X is,
and I
and
just
I just
say what
say
are
what
the
are the
x's.
X's.
Can't you
Can't you
calculate? No,
calculate?
right?
No, right?
yeah,
So
So
input of
input
this
of
is
this is
u of
U of
x.
X.
okay. So it is functional of, okay.
Yes.
Yeah,
Yes,
now I get
yes.
it.
And
And
then
then
there
there
comes
comes
the
the
let's say
let's say
when you say
when you say
scalar
scalar
valued and
valued
vector
and vector
valued, it
valued,
just
it
means
just
that
means that
uh, if the
if the
output of the
output of the
function is
function is
scalar, then
scalar,
it's
then
called
it's called
scalar
scalar
valued.
valued.
Implies
Implies
phi is
phi is
output,
output,
it's a
it's a
scalar.
scalar.
There is
There
a
is a
function,
function,
and the
and the
output is
output is
scalar.
scalar.
Input can be
Input can be
anything,
anything,
means
means
maybe
maybe
scalar
scalar
or
or
vector or
vector or
tensor,
tensor,
whatever.
whatever.
But if the
But if the
output is
output
phi,
is phi,
then it's
then
called
it's called
scalar
scalar
valued.
valued.
Same vector
Same vector
valued is,
valued is,
if
if
output
output
is
is
a
a
vector,
vector,
it's called
it's
vector
called
value.
vector value.
Input can be
Input
anything.
can be anything.
Okay.
Okay.
Uh, so
So
it can be like inputs can be anything and outputs can also be anything. Like you can give a input as vector and get output as scalar. You can just use the divergence. Then input can be vector and output you will get a scalar. And then input can be scalar, and if you apply gradient you can get the output as vector. So inputs and outputs can be anything, but just depending on what the output is, you call it as a scalar valued functional or vector valued functional.
Okay. And like in gradient we get generally vectors.
Yes, gradients you want input as scalar and output will be vector. Yeah,
Yeah, so independent. Okay. Now variation. Now,
yeah, we'll come to variation. So for function, function f of x is there, okay, and this is your function, okay, and this is your x, okay. So at a point you want to, let's say you want to find the maximum, or you want to find if you want to find the extremums, maximum or minimum, what you do, you take the derivative of function and say that will be 0
yeah.
and whatever point and get the point. So you use derivatives, right? What it means is, if you are changing x by just small quantity, how the function is changing,
Yeah.
and you just look for let's say this is your point. You say that at the peak or lower point, the variation, like the derivative will be 0. So that's how you get maximum or minimum, right? But let's say this is your functional. For the functional, its inputs are u, right? So this is x, this is u of x, and this u of x will go as input to f, okay.
Yeah.
So when you have input as x, you are saying I will change x by a little bit, and then see what f of x will be doing. But when you have u of x, what you say is I'm changing u of x by a little bit. So this, let's say this is u, and I'm saying I'll just change u of x, function of x is by a little bit, and you call this u of x as del u. And when you want to find the maximum or minimum, what you do is you'll take the first variation to 0. U plus del u is equal to f hat of u plus delta f hat at u, something like this. And you will make this one to 0. Same like derivative. Here how you do it is, it's f of x plus dx. You will say that it's f of x plus df by dx at x. And you want to make this one to 0, right? Same way, here it's like this is variation of u, and you want to make this to 0 to find the maximum of or minimum of that function. Is it fine?
Yeah, but why we are changing u? Like we can change x, like in the function we are changing x. We can
No,
here also.
no. Here input is x, so we are changing x. Here input is u, so you have to change the u. It's like when you want to find maximum or minimum, you are saying that when you change input, like change the input by a small quantity, how the output would change, like. And we want to say that output shouldn't change much when you are at peak. So input should be modified. That's why you keep delta u, not delta x. When you keep delta x, so for this u of x you will find what is it, but you don't even know what this u of x is, right? When you say this is a function.
Yeah.
So for a small change in u of x, and this input can be anything, like for all kinds of u of x you will have an output function,
Okay.
right? It's not just like for a specific test there is only specific u, and for that specific u there is a functional. For any arbitrary u of x there is a functional f dash. So depending on like arbitrary u of x, arbitrary function, not arbitrary but any function, let's say any function u of x, this functional will have, this is called function. For a specific function, let's say u1 of x, this functional will give some specific value, maybe phi 1. Okay, so let's say this is u1. So for this u1 it may be phi 1. Let's say this is u2. For this u2 this may be phi 2. Okay, and so on you will have any. So in general you are saying inputs are like u of x. Okay, output may be some function of x. So you want to find the some phi. So you want to find what will be the maximum. When is phi max? When is this like phi would be maximum for what value of input u, or when it will be minimum for what input of u. You get it?
Okay.
Question would be like when will f hat of q be minimum? We want to find what function makes it minimum.
Oh,
Makes the
adjustment.
functional. Yeah.
So basically, what I understand something, please correct me if I'm wrong. By this, we are actually making the error minimum in FEA.
Yes.
Oh, that's why we are using additional. That was my
Yes.
question.
That's why we are using.
Can you please show the above curve you draw? Just
Yeah.
yeah, here U1, U2, these are different functions.
Like u1 u2, yeah, different functions, but u of x can be anything, like any function you can say.
And phi is one is something we get after we
Something
put.
like output of that functional. Let's say if it's scalar value function, functional, some output.
Okay. And our goal is to find the minimum. So
Yeah.
we
So we
so
want to
we
find the minimum. So for what value of the function u, like for what function u of x, it makes the functional minimum.
okay, so that's why we find variation.
Yes.
Okay. But still, like but in equation how it comes like we were driving the equation there some variation we didn't apply variation, we just multiplied by weight function.
Yeah, like in derivatives, we when we say that when we want maximum or minimum, we directly say that this is how you find it. We don't talk about this method, right?
Yeah.
but this is
but
where
this
it
is
comes
where it
from.
comes from.
Similarly,
Similarly,
when you say
when you say
variation, you
variation,
directly
you
say this
directly say
one.
this
If you
one.
make
If
it
you
to
make it
zero,
to
you will
zero,
get
you
it.
will get it.
Okay.
So what
So
this one
what
would
this one
be?
would be?
Yeah,
Yeah.
let's
Let's
say,
say.
mm,
mm,
and
and
one lucky
one
thing is
lucky
all
thing
these
is all these
variations would
variations would
add
add
similar to
similar to
derivatives only.
derivatives only.
Let's say
Let's
this
say
is
this
your
is your
pi,
pi,
like
like
strain energy
strain energy
function,
function,
which is a
which
function
is a
of
function of
displacement.
displacement.
Okay,
Okay.
you want to
You want to
minimize the
minimize
strain
the
energy
strain
function.
energy function.
Mm.
It would be
It
like
would be like
delta
delta
pi
pi
is nothing
is
but
nothing but
you'll find
you will
something
find
like
something like
delta.
delta.
This is
This is.
so how you
So how
get it
you get
is
it is
something like you
something
will
like you will
of u plus delta u. Its sigma is nothing but c epsilon. C times epsilon times u plus delta u, epsilon times u plus delta u. And we'll just say that epsilon of u plus delta u is epsilon plus delta epsilon. Then you would get it as c first term would be c epsilon times this. Something like this. This one would be 0 because we are multiplying both very small things, and these two are same, and this one would be pi. So pi of u.
Oh, wait, this I don't get. Actually, when we apply variation, please come to first step. Yeah. So we take this variation directly to strain, right? What
Uh,
stress?
yeah, stress can be written in terms of strain, right? So we just take in terms of strain. Actually, it's supposed to be written in terms of u because u is the input, but still we write it as in terms of strain.
No, no, no. Like in the very first equation, del pi u is equals to sigma
Yes,
dot
here, right?
sigma. Yeah, here. So
Yeah.
in that, this del is directly applied to epsilon naught. Why?
Yeah, this is how you do it actually. In books, all you might see just directly this one, but when you do the method, this is how you do it. See, if you like, basically what you want to do is you want to find input as u, and you say this is my, okay, output would be, right?
Yeah,
So if you substitute this, you will have epsilon of sigma will be c epsilon times epsilon. And let's say you take this epsilon of u plus delta u is epsilon plus delta epsilon, and substitute this here. You have c times epsilon plus delta epsilon multiplied by epsilon plus delta epsilon. You'll get 4 terms.
uh, uh,
Right? Actually, pi is half times, right?
yeah.
So here
So,
it will be half will be present.
that's okay. But
Yeah, this first term would be pi
this
of u added.
epsilon u plus del u you have written it as epsilon plus del epsilon. How? Like
Yes,
this.
this one.
This this bracket. Yeah.
Yeah. So it's just an variation in u causes this much variation in epsilon.
Okay. Yeah. So we put it like this. Yeah. Yeah. Yeah, okay. Okay. And then we change it a little bit. Okay.
Yeah. So last
Yes.
term goes to 0 because it's very small,
Yeah.
and first term becomes pi of u, and second term is this is 2 times half will become c epsilon times delta epsilon d. So we are saying this is my delta pi.
Just a minute. I'm not sure. Yes. Okay. So that's why we have taken it directly inside.
Yes, this actually behaves same like derivatives only. If you see here, it's pi is like half times c epsilon times epsilon dv. If you take derivative with respect to epsilon, it's kind of like 2 times epsilon times derivative of epsilon, right?
Yeah.
In a similar way it behaves, but you have to be more careful. Sometimes it might deviate. Yeah.
Okay.
Generally, you might have seen this expression directly in many places.
Like in, but like in yeah, that is okay. But when we write the equation and and like what to do with like this bilinearity and symmetricity, that's only specific to these problems. Like when we move on to some other problems which are more complicated, then that's why we are just separating these issues. Here we are only getting into bilinear and symmetric problems, right?
Bilinearity. Why did those things come? Sorry. It's at least I would say bilinearity and symmetry, right? Yeah.
Yeah, why we need this bilinear and symmetric problems only? Like, is it
Yeah.
because the
General.
solution is specific to this problems? The
No.
solution we have developed.
The way we have derived the weight form, it makes it bilinear and symmetric.
Okay. Okay, and when we develop this thing in our equation, like in that we write that one side we get some bilinear function of u and v, and then minus some linear function of w, and that is
Yeah,
equals to 0.
something like you are saying. Generally, we something like this. You saw, is it?
Ye- no, uw minus lw is equals to 0.
Yeah. Yes. Yes.
Minus lw, please. Instead of b is for bilinear and l for linear. It is easy to understand.
Something is right.
Yeah.
Yeah, it's like the weight form would look like this. Only this one is bilinear. Yeah, it's like let's say in the bar problem, you're after writing it in this form, it was something like
A
dw
del.
by dx,
Yeah.
a du by dx,
Dx.
dx minus integral w.
Q dx.
It's not integral. It's just w q, like 1D problem. Like q2 minus q1 kind of thing, right?
No, no. Initially, you're writing it right. Like it is integral, and then one more time, W A du by dx. That their limits are applied. Like integral
Integral.
q W q dx, and then minus W a du by dx, a du by dx, and in this limit is applied from like 0 to L or something.
Is it?
Yeah, yeah, and this last two terms are linear.
Okay. This one is this is due to the external body force.
Yeah,
Sorry, just body forces, I just said.
body forces. Yeah,
Yes. This one comes because of this,
external forces.
no, like because of applying that UV rule kind of thing.
Yeah, but it
So,
represent external
yeah,
forces.
it represents external force. So these two becomes the function of W.
Yeah,
This one becomes the bilinear function in terms of U and W.
yeah. But what we get by getting this linearity, that's what I, like why what is the use?
What's the use when we say it's bilinear?
Yeah.
Okay.
Only thing is like at the end we say the K matrix coming out to be symmetric if it is bilinear. Sometimes we say it like this, but that is also not make sense. Like
It's I don't think both are same. Like if it's bilinear, it's symmetric. Nothing like that.
okay, so means what is the use of this bilinearity here? And it is also said that it is symmetric.
Yes, yes, it's both bilinear and symmetric. But, uh, uh, okay, I need to check this actually. I don't remember what's its advantages of this. But one thing when you say bilinear, it's like you can just mm, I think probably maybe this one. When you say bilinear, you can write alpha u1 plus beta u2 as like alpha p of u1.
Yeah, plus beta u two.
Yes,
Yeah, it is
this way you
linearity
can.
in U,
Yes, it's in linearity in U. So
and then
probably we are trying to use this one, right?
yeah.
Substitute this into this. Maybe somewhere like that. Maybe it's better. I will just check it back and come to you about this next week.
Okay, and
Linearity and okay, I will check this and I will tell you next week.
okay, and like this variation thing that we have just seen,
Yes.
that is not going to come in picture when we are actually calculating like turning wheat forms and doing the stuffs. Like when we are doing the FEM formulation, we are not going to get this thing like variation is equals to zero or something. But
Uh, when you take these weight functions, you are multiplying with weight function, right?
yeah,
That's basically a variation. That's it.
oh, so it is a variation.
Yeah. We just say that it's a weight function. That's basically a variation. I will explain this term once. Okay. Let's say you have this x and you have any arbitrary u of x. especially for, let's say we have this bar problem, okay, and we applied some U1, let's say U cap load displacement at this end. So we know that at this boundary it will be U will be 0 always, and let's say this one it's some U cap. Okay, we definitely know that U will be 0 at left point and U will be U cap at right point, but we want to find what will be the U of x will be in between. That's unknown. It can be anything. Okay,
Yeah.
that what this U of x is, we want to find out. Okay,
Yeah.
and when we are saying it's variation, so as we know at these points is U is same, so the variation won't be present on those points. It's known. Only variation will be present at only unknowns. So W will be 0 at these points. So just in between this, it's variation, something like this. It would W of x would be. That's the reason why when we say weight function, we say that W is 0 where U is known, because W is variation of U, and where U is known, it's like we won't have to find its like variation.
Okay. So yeah, but it's still like we need to. So when we are multiplying by weight function, we are basically multiplying by variation.
Yes.
But we can take this variation anything, like in some different method, we take different variations.
Yeah, you can take this. You're saying this one. W. W
Yeah, the
can be
W.
anything arbitrary. W of x arbitrary any function. Just it needs to satisfy this condition. Function that is equals to 0 where x is known. That's it. Yeah.
Like before moving last to the last point, like one thing is
Yeah.
we make weight functions. Matlab weighted means weighted error is equals to zero, right?
Sorry, we make.
Weighted error to be zero.
Yes.
Like why we make with this weighted error, like why we go for weighted error, like we can have this positive errors plus minus plus, like we have a set of positive error and we have a set of negative errors in the same element. Summation should be zero. That also give
Oh,
us
there's the catch. You are saying, let's say this weight is sometimes positive, and let's say other case it's negative, so they both cancel out and become 0.
yeah. But even if we don't take weight, we simply take error, then also the same thing is true. Then why we go for weighted error?
Actually, when you say this is 0, at each and every point this becomes 0, like error becomes 0, not just the whole integral. Because when we say this for any arbitrary function, this is 0, means the other integrand should be 0.
I don't understand what.
Like we are saying for any W of x, focus on this point, and we say that W times whatever error dx is 0,
Yeah,
right?
yeah,
So you want this whole integral to be 0, and this is like any function, any arbitrary function. Okay,
yeah.
so if this it is possible only when it is possible, only when E is zero everywhere, right?
Yeah.
That's why we take it. If let's say we don't have this arbitrary function, then your case is valid. Like it may be negative and positive error, then whole integral might be zero.
No, no, no. That is what he like it was told in the video. Like because we are not able to make that zero, some positive and some negative error clubs together makes the total error zero.
Wait, no, did it? What exactly did sir say?
He says like because we cannot make error zero at every single point. So in an integral sense, we make error zero. At some point it is positive, at some point it is negative, but the total integral comes out to be zero.
No, it's like when we say this and when you take arbitrary function, that error will be zero at every point. It's not.
Like multiple
It's not.
times he says the same thing, like that we are not going to make the then that is the he said the concept of
Then it's like something like error. If you take half of that, then it would be like solution wouldn't be correct. Right? The whole point of this adding this arbitrary function before the integrand is so that whatever the error is, that it will be zero everywhere. Maybe if you like know which value is it might become something different or something different.
yeah, like in many videos he said repeated same thing like in first part also in this part also he said like because at every point it is not possible to make error zero. So that's why we are taking it into integers like I can suppose it, right? Repeated error zero integer. Double equation. Yeah, lecture 25.
Thank you.
Five, yeah.
It's uploading.
Yeah, 100 to 16 minute. Yeah, yeah. So a little bit more than yeah,
So this is
yeah, predicted entry is 0. Error is not 0 at every specific.
over element is 0. So the error is not 0 at every specific point, but the weighted residue over the entire element is 0. So kind of in a sense, then the error is 0 in an integral sense over the entire element. So this is, so let's call this equation A and we will call this equation B. So
I'm not sure.
now what I do is I plug in this equation in equation B to get.
Weighted residue over element is.
So before I
Because the error is 0
I
at
wanted
all the
to
points, then it will
make you understand
like it is
or explain
that
clearly
solution.
that in one dimensional system we were integrating it over the
And
length of a element which was a straight line.
sometimes it's like even with FEA, uh, there are different methods. This is like a variational method, whatever I said, and whatever professor has said, it's called variation weighted residue method. Both are ultimately what they want to do is same and similar, but the way they look at things might be different. Here, whatever I told you, I came from a perspective of a functional, and I want to minimize the functional and then do it something like that. Minimize the functional, something like that. They might come with as error is this much, and perspective might be a little bit different, but I will check it and let you know what
I have a I have a thought project. You will please tell me if it will be right. Like I'm just trying to make like how we are like we are looking into data integral. Like if it takes this as well as this weight is variation.
yes.
So basically we are thinking variation of error 0,
Uh,
right? So
yes.
in an integral sense, like in an integral sense, the above curve you have made it may go up, it is going up and down. But in an element, it is just an element, like what we are showing. So in an integral sense, the variation of this error or variation of this is a curve of error, not you. So from original to this, the difference multiplied by variation. That variation in an integral sense is zero. So we get a very close curve to what exactly we might be. That is using that variation.
Yes, actually till here, whatever you are solving till here, it will get exact solution. The difference comes when you approximate the function in this way. This is where you start approximating. Before this point, everything is like no assumptions are there. Whatever you are solving before this point, it's like exact solution you should get.
Okay, so
This is where approximation starts.
then it will not be improved. Like what I am saying is like this statement itself is like getting some approximate you.
Yeah, approximation starts here. So, so before this, if you have the weight form, let's say you are here and you didn't take any approximation till yet, then if you solve this integral as it is, then you will get the exact solution.
then the whole point of this statement in error is just be zero. Then but then it will completely contradict from the statement what he is making.
Yeah, I will check the video. I didn't watch the video actually. Maybe I'll just check it.
Yeah, because in one part one also the prepare he is continuously make this statement multiple times, like this thing.
Okay. Okay.
And that because we are not making able, we are not able to make this error as zero. Because zero is already approximated. We are not looking into the exact function. Like
Okay. I think, yeah, as I said, sometimes different methods are there within FEM also. This is like variational method. Like you start with functional and you want to minimize the function. Here it's not the error, it's directly strain energy. You are minimizing the strain energy to get the solution. Something like that. But everything boils down to same thing, but perspective of looking might be different. But I don't know what like from where he started. Maybe approximated beforehand itself or something like that.
no. He is approximated that point only. He said multiple times that again after some point when we go for geometric approximation, he told the same thing that you told that we start making assumptions and we assume Q.
Yeah. So it's like when we start this assumption, then only there will be error comes into picture. Till this point, as far as I know, I can say that error will be zero everywhere. When you try to solve this error will be zero everywhere.
Please check it and this and bilinear thing. Why we need bilinear?
Yeah.
Yeah, and I will go here read one again, and then I will ask like because there's one thing related to it, like how we decide the primary variable and secondary variable.
Yeah, what I didn't understand the question.
Yeah, actually, it was told in the recent video that while making this 2D formulation. Yeah. Yeah. The wave function represents the variation of primary variable in this case. And it help you know u previous and help you know u which is a u that is the primary variable. Like by looking into weight function we can actually tell what is the primary variable.
No, it's no. You need to by looking at weight function, you can also based on the primary variable, you will what the like both are not related actually. Weight function and primary variable.
Why he didn't specify. Yeah, that is actually what he told that he has this boundary term. And
Yeah,
boundary
actually, it helps in finding the secondary variables. What your not secondary, what your boundary term should be.
yeah, secondary variable that will be. But what he told that boundary term will have two components. One is W,
Yes.
the other part.
Yes, this is first part and this part is second. So it's like this one is about Dirichlet boundary condition, primary boundary conditions,
Yeah,
and this one is secondary boundary condition.
yes, that is what he said. So while talking about the primary boundary condition, this primary, this W he says that since it represents the variation in primary variable,
Yes,
W.
yes, and it will be zero when primary variable is known.
Yeah. So that's why it's helpful to tell what is the primary variable. And if we specify this W or U, then we are that's we are specifying the essential boundary conditions.
Yes, So here, if you like in this equation, no primary variable is q. So if you have boundary condition on u, then you know where, like what is, let's say w will be 0.
What? If
We know that u is primary variable, and let's say in some boundary condition you have u is u1, u2, something like that boundary conditions.
yeah,
Some it's 1 and it's 2. So at this point w will be 0.
so what we do was just like k is zero, but we don't make use of this.
No, we do make use of it. So these things comes into picture when you apply boundary conditions.
Yeah.
So if you want to find something like yours is w a d u d d x, it's 1 and it's 2 1, and this one. Let's say your problem is simply separated problem. Okay. So in case x1 and x2, u are u is 0. Then w is also 0. So this whole term goes to 0. And let's say you have this kind of problem. Okay.
So it will give one boundary condition. That is what you are
Yeah.
trying to.
Yes. Here u is 0. So at this point, the term at x1, this term would be 0, but at this one, this will become 1, and this will become this will become 1 because again we write w as ni wi, and wi excludes away large body if you remember, and this ni would be 1 here, and we get whatever this term is there will be remaining.
Yeah.
Something like that.
Okay, so when in the first case when this is simply supported, there we don't need natural boundary conditions.
No, it's kind of highlight the natural boundary conditions. This is what it is.
No, we applying w is equal to 0. So that means we are like primary, very makes essential boundary condition we are applying.
Uh, yes, primary boundary condition. So you will finally you will have something like AU is equal to F format. Okay. This one. Okay. Maybe maybe next week we can see one problem in 2D case how this boundary condition also will look like, and how it gets applied. Then will
Yeah. So the bilinear thing and this actually we make approximation and this thing like essential and how we
Yeah.
So
this term comes into right hand side. So these things help. We use substitute these things and find out if actually. Yeah, maybe like we can talk about bilinearity, symmetry, and then error and boundary conditions. And then as well, maybe it's by some sudden, maybe by Friday if you have any other doubts, you can just mail me. I can prepare accordingly. Then 6 and it will be more useful for me.
yeah, sure. Like